All right, can everybody hear me? Yeah, I'm loud. All right, thank you for waking up on Saturday and joining us for breakfast and making it in time for the first talk. It's strange to introduce our next speaker, not because he's strange, but because I think some of my earliest memories of this field are, or it feels like it wasn't that long ago that we were both here as like first or second year PhD students meeting in places like MLHC, and now Tristan as an organizer, introducing him as an invited speaker. Tristan Naumann completed his PhD at MIT in about 2018, has been working as a principal researcher at Microsoft Research, and has worked pretty extensively in this field, both on a lot of classical tasks like predicting readmission, predicting mortality, various things with health records data of hospitalized patients, but also on creating sort of large-scale resources at the intersection of things happening in natural language processing, like large-scale embedding models and clinical data. So excited to hear his talk, and without further ado, Tristan Naumann.
So, hi everyone. Yes, thank you, Zach, for the introduction. As you mentioned, I'm Tristan Naumann. I'm a principal researcher in the Biomedical, Natural Language Processing, and Real-World Evidence group at Microsoft Research's Health Futures. And I'm quite excited to be talking to you all today about natural language processing for healthcare. So, as Zach mentioned, we've both been here a few times. So let me paint a bit of a picture here. So. For those of you who know, this is MLHC about 4 years ago, maybe 5 years ago in New England, or perhaps for those of you who don't know, but if some of you were there, you may have encountered someone walking around, you know, sort of saying, hey, so, you know, that sounds like it could be an NLP problem. Incidentally, that same person may have tried to convince you that every problem was an NLP problem. And I won't, that, you know, full disclosure, that was 100% me. I won't try to do that today. But what I would like to do is sort of share some of the motivation for how I got really excited about natural language processing. Also maybe share some insights from the recent clinical natural language processing workshop, and then talk about some of the work that our group is doing in this space. You know, and in part, I won't try to share that same viewpoint because we have some excellent interns who over the past few years have tried to convince me that actually maybe everything is a graph problem and have made some good progress in that direction. So I got really excited about natural language processing in part because I really looked at it as this way to unlocking the future of medicine from clinical text. So if you consider, for example, many of the things that we know are really important measures, we have instrumented ways as a society to measure those things with really high frequency and really high fidelity. So consider something like heart rate, for example. We know this is an important measure of cardiovascular health. We have found ways to measure that in care settings extraordinarily well. Everything else that we think might be important all just gets relegated to notes. And I think what was actually really nice, especially from the poster session here yesterday and sharing various anecdotes, is occasionally sometimes the notes also just contain the truth. So there was an excellent example from a former lab mate of mine, Willie Bogue. I encourage you to sort of ask him about the specific anecdote. But you know, this sort of setting where a nurse is prompted to provide some structured information, and that structured information was actually just inaccurate each time because this was really a burden at the point of care. And so what the nurse had done was just immediately sort of X'd out of all of the things for collecting that structured information and said, you know, what we'll do is we'll actually just record that important information in the notes. And so this is also a case where often if you're looking for the truth, you might find the full story in the notes somewhere. And I think, you know, one of the things that I was heartened by in working in this space was that time and time again, we saw this really similar story. So these are two very different studies. One is on this I2B2 data set. Another one is in the development of an automated sepsis trigger. But the story that emerged time and time again was that you saw this progression where using NLP, You were able to get performance, predictive performance often is what people were looking for, out of some of the unstructured data, the clinical text. Often it outperformed some of the structured data, but irrespective of whether it outperformed the structured data or not, the combination of the two outperformed each one individually just because there was so much complementary information to be gathered by both. And so this was a really nice setting to be working in, where there were a lot of, maybe even just easy wins because we were incorporating another source of knowledge that really allowed us to push the envelope further with respect to what we were able to predict. And there were a lot of people who sort of saw the same thing, and it sort of spawned a sub-community in the NLP space. And recently we held the fourth clinical natural language processing workshop co-located with NACL, which is a large NLP venue. And I thought what would be really nice is to sort of share some of the insights that emerged from that workshop here, and then connect that to some of the work that our group has been doing. So I think at a high level, there are sort of 4 key takeaways. There were many more discussions that of course occurred, but there were sort of maybe 4 key takeaways. One was there really is this pretty dramatic difference between general domain and the biomedical and clinical domains, collectively the healthcare domain. In some cases, this is, expected. In some cases, this is not a great thing. In some cases, there are opportunities for healthcare to better inform the general domain NLP. There's also this acknowledgement that NLP is having a bit of a moment. Like I think it would be, I would be hard pressed to imagine that most people in this room have not heard of things like BERT or GPT. They've, pervaded a lot of everyday settings for us, but they have also, fundamentally changed a lot of what we're looking at in NLP. And so it was, how can we take advantage of this moment? Something that also resonates quite well with my experience in the MLHC community, this focus on real world impact. So even though we might be focusing on these sort of more technical problems, we really want to connect them to some sort of real world impact. And then the last one, which I maybe wasn't expecting as much, but was really nice to see, was that there is often this sort of connection between problems that emerge commonly in natural language processing and problems that we have in the broader machine learning for healthcare settings. So in many of these cases, there might be this natural framing that NLP provides for how to solve those problems. So let's talk about the first one. One of the things that was really nice about this workshop, Mark Dredzy did a wonderful opening keynote on rethinking clinical NLP. And as part of that, he had broken down a sort of a brief history of NLP, progressing from an initial era where we started off looking at, what we might think of as traditional NLP, rule-based things often, focus on grammars and syntax and things like that. The sort of shift to the second era of statistical NLP, where we were really looking at, how can we leverage data in order to really improve our underlying performance in a variety of the classical NLP tasks. And then sort of this third era where we're looking at large language models. And one of the things that he had sort of pointed out as an initial gap was that clinical NLP has often lagged behind the general domain, in part just because of data availability. And this isn't surprising. I mean, anybody who has tried to work with clinical notes, I'm sure has come up against some of the same barriers. But really what stood out to me was how much of a gap there really was. So if you think about some of the common resources that have pushed forward general domain NLP, things like Penn Tree Bank, that was 1992. If you look at sort of similar corpora in the clinical space, you might have something like I2B2 with respect to the same number of annotations. That was 2006. So we were really held back for a reasonable amount of time. And because of that, clinical NLP developed in its own direction, really focusing on a lot of the existing rule-based and sort of specialized systems. And I want to highlight, this is not necessarily a bad thing. It's a very different direction, certainly. But there's a lot of knowledge encoded in some of the same rule-based systems. Another thing that is really interesting with respect to general domain versus sort of this healthcare domain is actually just the underlying language that emerges. And so in some recent work on biomedical vision language processing, this was sort of called out explicitly that if you're considering paired image language, or paired image language or paired image text, we often have things in healthcare like chest x-rays, for example. This is very, very different than what you see in the general domain. So, if you look at this bottom example, you have a pretty short caption. It's very descriptive. What you don't see in that caption is anything like, this image does not contain a cat. That might be pretty common to, there are a lot of images that contain cats, but in the top one, you really have this emphasis on structures like negation that we actually know are challenging for the broader NLP tools that we have currently. So, there's been a lot of explorations, for example, into things like BERT about how does it handle negation. And so between things like complex sentence structure and the use of modifiers that are prevalent in chest x-rays, those are two that are sort of called out in this work as being specific challenges for chest x-ray and this sort of paired image text modality, as well as expressions of uncertainty in the classic sort of things like class imbalance, really. There's just a dramatic difference between the types of language that we see in healthcare settings and general domain. What's really interesting to me is that if we solve some of these challenges in the healthcare setting, those will probably translate quite well to general domain as well. They might not be, as necessary. So some of the things like negation, maybe they're just not as necessary in general domain, given the types of data that we work with. But the wins in the healthcare domain will translate back to that domain as well, general domain. So let's move on to, like NLP is having a bit of a moment. I think, like I said, I would be hard pressed to imagine that most people here have not heard of BERT. It's basically provided a new NLP pipeline. And so I think one of the nice things about that same keynote that Mark Dredze had given is that he had sort of outlined this third era, that's the emerging era, where large language models really take over. And what's interesting about this, and maybe for everyone here as well, what might be interesting is even if you've not been part of the existing NLP community for a long time, this is an opportunity where using some of these tools is incredibly easy. There are platforms like Hugging Face that have made this, incredibly accessible in exceptional ways. If you're thinking about biomedical and clinical problems, there are now a plethora of really high quality resources that you can get started with across a variety of subdomains too. If you're looking for something in radiology, you can find something specific to radiology. If you're looking for something more general domain EHR, you can find something like that. And of course, you can also sub in some of the general domain tools as well. There's also, this emphasis on sort of autoregressive models, things like GPT, that really form the basis for a new mechanism of modeling different types of tasks. And I think, this is actually a really interesting example. This is from a paper recently by Agrawal et al. I think what's really fascinating about this is that you're using a language model, but you're using it to do an information extraction task. And the same paper has other examples for things like summarization, question answering, as well as a number of others as well. But this example alone is actually this is something years ago I probably would have said that you couldn't do. And seeing it done is actually quite impressive, really, for a variety of reasons. So the specific thing that's happening here is, you're asking this model as a language modeling task to pull out information about this context that's been provided to it, this input. And it's able to do this in a really robust way. There are, maybe a couple of caveats here, but I think the thing that was most startling to me about this is I remember talking with the authors and saying, wow, these are some really great cherry-picked examples. And then going through and trying it myself and realizing, wow, this actually works way better than I thought it was going to. This is actually, like, for many counter examples I can provide, unless I'm trying to do this adversarially, this is actually working reasonably well. So let's also talk a bit about the real world impact. So, again, this is maybe no surprise to this community. If we're working with NLP, it also needs to fit into end-to-end scenarios that we care about. We're going to do this often through deep partnership with stakeholders. And we want to have sort of rigorous and continuous evaluation on real data. And so later in this talk, I'll maybe talk about two partners that we're doing this with, Jackson Laboratory and Providence. And then finally, I think one of the things I'd mentioned is how NLP can provide this broader framing for a lot of problems that we care about in healthcare. So, the classic one is maybe this annotation bottleneck. So hiring experts to scale, as we've heard yesterday and certainly in the past, it's really not scalable. And so the classic thing that we do in general domain is we say, let's crowdsource it, right? I will tell you right now, I have a hard enough time finding the traffic lights. There is no way that I could do this without just hitting skip until I got a really easy one. So this is really just off the table in a lot of cases. And in part because of that, this is a problem that we see in machine learning for healthcare, but it's also a classic problem in NLP. And so we've developed a lot of tooling to work with unlabeled data and domain knowledge. And so, maybe in other words, what we often want is this like familiar, nice, supervised setting that we're all comfortable with. This is pretty common, but we can't do this because of this bottleneck on annotations. And so what we've done instead is we've found ways to use this this abundant unlabeled text and create task agnostic resources. And then also to use domain knowledge that we have about specific tasks, so task specific knowledge, in order to develop algorithms to create application models. And really the goal of many NLP papers in the past has really been, how do we use all the sources of signal that we have access to in order to use the best of them and come up with something that works, exceptionally well. And so this framing is really nice, I think, for a lot of the problems I've encountered where we're talking about, hey, I want to do this patient modeling task, but I actually don't have real labels. I maybe have this proxy, but it's not great. It's a really noisy signal, et cetera. So I think with that, let me talk about some of the work that we've been doing in this space, starting off with some aspects of domain-specific pre-training, which really reflect that right branch before task-agnostic resources that we want to use across a variety of downstream tasks. So many of you are familiar with BERT. For those of you who are not, a really quick intro. One of the things that we're doing is we're looking at how we can create self-supervised tasks to come up with better language models. And the way that we're going to do this is we're going to start off with some text, and we're going to say, well, we don't innately have a label here, but what we can do with nearly any text really is we can just mask out some words, and we can construct this new task that is effectively, I give you one of the words, predict another word, maybe early on some things with next sentence prediction for continuity. But the idea is really, we're finding a nice task that represents a proxy for some of the prior conditional language models that we used previously. But conveniently, it's one that allows us to take into account much longer range dependencies and also some other aspects of language that we were unable to capture before. And so there's a lot of work in this space, but previously a lot of the work had really focused on this idea that what we want to do is leverage forms of transfer learning, really start with general domain, do this process called continual pre-training on some subdomain, come up with a new model, derive a new model that will work in that subdomain. And this does, actually quite well in many domains, especially when you have, limited unlabeled text in your new domain. But in healthcare and in biomedicine, perhaps, we actually have a lot of data in the form of, medical papers, things like PubMed. So what you can imagine pretty quickly is, how can we actually just construct from scratch one of these new resources? And that's one of the endeavors that we set out to do, is create a specific BERT based on PubMed. And to see why this is actually why this might be effective, at least build some intuition for why it might be effective, you can look at the vocabulary of some of these models. So all of these models use this sort of word breaking scheme. There are a couple of different ones, but the idea underlying this is really, let's break up words into smaller subwords, and let's use that to mitigate some of the classic NLP out of vocabulary issues that we see. If you look at a lot of things like BERT, for a lot of medical terms, it's actually going to break them up. So at inference point, you actually have to shift a lot of that to the underlying network in order to recover some of that performance. There are endeavors like SciBERT that really aim at how can we do sort of training from scratch, and how can we specifically do that with PubMed, but then also with computer science papers, since they get weird word breaks as well. And what we see at a high level is that training from PubMed incorporates a lot of these common vocabulary just directly into the vocabulary. And unsurprisingly, so for a set of biomedical benchmarks we care about, PubMed BERT does extremely well. What's nice is that in constructing this sort of benchmark set of tasks, we're able to test a lot of these other BERT-based models as well. And so we can see things like BioBERT actually does quite well on a variety of tasks also. What's nice, of course, is since this is a task agnostic resource, we can transition it over to some COVID specific things, form the basis of a biomedical search tool, and do quite well there also. And of course, one of the things that I believe really strongly in is trying to share some of these models. And so this is something that we've made public so that other people can use it and do new things with it as well. But this is only really the beginning. There's a lot of things where you can further improve some of these models and really push them further and further to see, increasing gains, although somewhat marginal relative to the initial leaps. So I'm going to transition a bit into task-specific things. So I'll run through these quite quickly, but I think these are quite interesting because this is sort of that other branch, that left branch of how do we leverage domain knowledge. And in the initial one, we're going to be talking about a molecular tumor board scenario. In assisted curation, our goal is really not to replace some of the people who are doing these curation tasks. Many of these settings are safety critical, or at the very least require some degree of human interaction. And so the goal is really help empower the people who are doing these curation tasks to have super speed, triage the information that they're seeing so they can make better decisions more quickly. The molecular tumor board problem at a high level is it's very difficult to scale. It requires reading through lots of literature to identify the best treatments for some of the patients that are being seen. This might seem trivial, but there is a volume of information available in PubMed that is absolutely overwhelming. And you might say immediately, well, they're not all about cancer subtypes or anything like that. But even if we look at just specifically some of the cancers, there's a rapid growth of literature in this space as well. And so it's still infeasible to actually go through and read a lot of this information. And so one of the things that we might want to do is just say, well, look, we know you're reading through this information, looking specifically for these relationships between, genes, mutations, and drugs. So can we help you do that? This is interesting from an NLP standpoint because we're looking at relationships among three things rather than the classic between two. But it's also actually a really tough thing with respect to NLP because there's this long separation in many of these documents about where the drugs, mutations, and genes occur in the document. And so, for example, the drug and the mutation never occur in the same paragraph. And you might say, well, that's a really tough example. Maybe we just miss those ones from an NLP standpoint. But this is actually a really prevalent case, but it's one that general domain NLP doesn't cover. And so we looked into, a number of mechanisms for overcoming this like sort of bottleneck of high recall. And in some of the earlier things that we considered let's just use BERT, but this is really tricky because it doesn't handle long text spans really well. We also looked into, how can we better get better supervision signals, but there's this sort of lack of direct supervision. And then also just sort of what are some signals for distant supervision as well. And it's very noisy in this case, so it's very difficult to do as well. We had some initial steps in this direction. They worked, reasonably well, but they were limited to this sort of context window of about 3 sentences when searching for relations. We expanded this to work across whole documents, which is, definitely a huge win with respect to the underlying NLP technology, but maybe didn't have the same impact. And we finally landed on a solution where we're really looking at this mechanism of modular self-supervision, where we're decomposing this problem into argument resolution and relation detection. What's really nice about this is that from the text, in this decomposition, we're able to do explicit discourse modeling, so leverage some of that domain knowledge, find the things that reside in shorter text spans and combine those. And we end up with something that is both less error prone, and then also something where the gains that we see are tremendous. So about 20 points with respect to F1. And of course, this doesn't completely overcome this, but it certainly addresses some of that bottleneck. The really nice part though, is in working with our partners, we're able to substantially reduce the amount of time that they're spending on this task. So we did a user study with them. And what we're finding really is that what previously were thousands of expert hours collectively for a single drug are being reduced to on the order of about an hour. All right, so I'll talk really briefly about another task, specifically task-specific self-supervision for real-world evidence generation. And in this case, we're looking at identifying key tumor attribute information from patient records. So Patient records, this is a variety of different types of clinical notes in an oncology setting. And what we'd like to do is identify T&M criteria. So things about the size of the tumor, nearby lymph nodes that have cancers, and whether that cancer is metastasized. And maybe unsurprisingly, if we start with some of those, task agnostic resources that we developed previously and fold in some of the things we know about this space, we are indeed able to do quite well. So we can develop sort of a subsequent BERT derivative from PubMed BERT, this oncology BERT, OncoBERT, that's able to extract these types of information for collaborators at Providence extremely efficiently. Moreover, what's really nice about this specifically is in our goal really toward creating something that will allow those same curators to not only identify that information robustly, but be able to identify where in the note that information arises. We're able to develop some tooling that allows them to see not only what is the information that was identified for this patient, but where in their record can they find it. All right, so with that, here's another image of a prior machine learning for healthcare. I've been thinking a little bit about what is the future of NLP and more broadly machine learning for healthcare. It is almost certainly in this room. And so one of the things I wanted to just remind everyone of from the opening notes yesterday is that, especially this being one of the earlier in-person events that I think we've all had together, this is an event that was extremely formative in my development as a graduate student, and later on has just been a resource for inspiration. So I would encourage all of you to collaborate, try to gain the same from this as well. And with that, I'd like to thank some of the direct collaborators in our group, as well as some of our partners externally and the former interns we've had. And I'll end there.